Today, we're diving into a real scientific head-scratcher. It's a measurement mystery that has huge implications for everything from developing new medicines to keeping us safe. How can two identical, top-of-the-line instruments looking at the exact same thing come up with two totally different answers?
So, let me ask you this. Picture two brand new state-of-the-art machines, straight from the factory. You feed them the exact same sample. You'd expect to get the exact same result, right? I mean, that's just logic. But in the real world, the answer is often a surprising no. And that's where our story really begins.
And here's what that problem actually looks like. You've got Lab A on the left with one result, and Lab B on the right with a slightly different one, even with the same setup. See how the peaks aren't quite the same height or in the exact same spot? Now, this isn't just some tiny academic quibble. When you're trying to identify the chemical fingerprint of a new drug or checking for dangerous contaminants, close enough is absolutely not good enough. These little differences can cause some really big problems.
The technique we're talking about here is called Raman spectroscopy. Basically, you zap a sample with the laser, and then you measure how the light scatters. This creates a unique chemical fingerprint for whatever you're looking at, kind of like the graphs we just saw. It's an incredibly powerful tool, especially in the pharmaceutical industry. So you can see why it's so important that every single instrument speaks the exact same language. Public safety literally depends on it.
So, how do you fix this? How do you get every instrument in every lab all over the world to agree? Well, you need a rule book, or let's think of it as a universal recipe, a set of instructions that anyone can follow to get the exact same result every single time. And believe it or not, that's what the global scientific community has been trying to write for decades.
Now, this universal recipe book really has three main parts. First up, you need a dictionary, right? So that everyone agrees on what all the words mean. Then, you need really clear instructions, that's the calibration part, to make sure everyone's kitchen tools, so to speak, are set up the same way. And finally, you need a taste test, or what scientists call validation, to prove that the recipe actually works. Let's break those down.
Okay, let's start with the dictionary. This is hurdle number one, and it's a big one. You'd think agreeing on words would be easy, but take the term Raman spectroscopy itself. This one concept is defined in at least 3 different major standards, from big organizations like ISO and ASTM. And guess what? Sometimes those definitions are just different enough to cause confusion. I mean, if you can't even agree on what to call the technique, how are you ever going to agree on the measurement?
All right, on to part 2 of our recipe, the instructions, which is all about calibration. Think back to those graphs. The line along the bottom, the x-axis, measures wavelength. The line going up, the y-axis, measures intensity. Calibration is just the process of making sure that every single instrument's ruler for both of these axes is exactly the same. Without that, one machine's idea of a centimeter might be another's idea of an inch.
So how do you actually calibrate your ruler? Well, you need a perfect, unchanging reference point. A golden ingredient, if you will, that you can measure your own instrument against to make sure your ruler is telling you the truth.
In the measurement world, this perfect ingredient is called a certified reference material, or a CRM. It's a sample whose properties are known with just incredible precision. The idea is simple. You pop it in your machine, check your result against the official certificate, and tweak your settings until they match. It's basically the scientific equivalent of the official kilogram in Paris that all other weights are measured against.
But here's the twist. What happens when the people who make the golden samples don't entirely agree? This chart here shows the accepted value for a key measurement in polystyrene, a really common CRM, from 3 different international standards bodies. And as you can see, their accepted ranges, they don't quite overlap. So even the very tools we use to standardize everything aren't perfectly standardized themselves.
And that brings us right to the heart of the matter. People have been working on this for years, but that universal recipe for Raman spectroscopy, it's still very much a work in progress. When you zoom out, you see this whole landscape of gaps that still need to be filled in.
And hey, you don't have to take my word for it. This quote from a 2022 paper in Applied Spectroscopy sums it up perfectly. It says, "The standardization landscape is incomplete and has not been modernized according to the developments in Raman spectroscopy techniques." In other words, the science is just moving way faster than the rulebook can keep up.
So, where are these missing pages? Well, there are a few big ones. A lot of the existing standards were written for older instruments that hardly anyone uses anymore. There are almost no rules for brand new, cutting-edge techniques. And get this, there aren't even certified materials for some of the most popular lasers people use today.
On top of all that, the CRMs that do exist can be super expensive, and their certificates often expire in just a year, making it a real challenge for labs, especially those with fewer resources to maintain consistent quality control.
Okay, so it sounds like a big challenge, and it is. But the story doesn't end there, in a mess of mismatched data. The scientific community is actively working, together, to finally finish this recipe.
The key, it turns out, is collaboration. Big international projects like VAMAS and Charisma are bringing everyone to the table. National labs, universities, private companies. The goal is to bridge all those gaps we talked about, to update the old rulebooks and to write brand new chapters for the latest technologies. All to ensure that in the future, Lab A and Lab B can finally get the exact same answer, every single time.
Which leaves us with one last really fascinating question. You see, writing a rulebook for science is a super delicate balancing act. You need rules to make sure results are trustworthy and comparable. But you also need to leave room for freedom, for innovation, for the next big discovery. So the ultimate challenge is this: how do we standardize science without accidentally shutting down the very innovation we're trying to measure? Something to think about. Thanks for joining me.